Power is the rate at which work is done. Welcome to Edu-ca-te. Today we're going to be introducing the concept of electric power. So what is this definition actually saying to us is that power is the rate. Remember that when we've got a rate, we talk about the speed or how fast something is done at which work is done. So here we're actually talking about how fast is work done. So how fast work is done actually depends on the power of a certain electric component. Okay, so here let's focus here on the equations of power. So here power is equals to W over delta T. So this is the original equation, which is actually from this definition that states that it is the rate at which work is done. Okay, let us look at these symbols. P represents the power, the electric power, and then W represents the work done, while delta T represents the time. Remember that whenever you've got something with a rate, it means that you're dividing by time. So here it is the rate at which work is done. Okay, what is work done? What would we put under work done? So work done depends on how much energy has been transferred to an object. So here work done is also called energy transferred. So if a high amount of energy is transferred to an electrical component, therefore it can do much work. Just like a refrigerator with high energy, it means that it can do super work. So here, our power is given by the symbol of watts, while the time is symbol seconds, and the work done or the energy transferred is in joules. So this is the whole power equation which we have. So we've got other power equations like P is equals to VI. So P is equals to VI, you only use it when you are given the voltage and the current of a certain electric component. So here, remember that voltage is talking about the energy transferred to each charge so that it can move. And then current is the rate of flow of charge. So here, what if you were not given voltage, nor were you given current, but you're given resistance? Well, we have got another power equation. Remember that the Ohm's law states that V is equals to IR. So it means that here when you see V, you can actually replace it with IR. Therefore here you can write IR times I. So this is the same as I times I is I squared and then R. So power is also equals to I squared R. This is our third power equation. So here, what actually happened from this equation, you can use this equation, is fine, but then this equation can only work when you've got the voltage of a certain electrical component. But then if you're not given the voltage, but then you're given the resistance and the current, therefore you can use IR, because IR represents the voltage according to the Ohm's law. So IR times I is equals to I squared R. That's why this is another power equation which you can use. Therefore, if you are given current and resistance, always use this one. And then we go to the fourth one. We're actually going to denote it from here. So it's going to be derived from P is equals to VI. So here, what if you are given voltage indeed, but then you're not given current? According to Ohm's law, you know that current is equals to V over R. So here you can actually replace current with V over R, because you have got voltage, but then you do not have your current, and you do have your resistance. Therefore here you can say V times V over R, whereby V over R is actually representing the current of that of that electrical component. Therefore V times V is V squared, and then this is over R. Therefore this is our fourth power equation. P is equals to V squared over R. So these are the basic equations we're going to use when you're calculating something related to electrical power. Thank you for watching. Don't forget to subscribe. Tell your friends to stay tuned.